Swayam Prabha. Digital India. Educated India.
Hello everyone, and welcome back. We are going to get into the first laboratory session of this course today, and we are going to talk about preparation of geologic sections from geologic maps in this particular laboratory. We have already looked at the salient features of geologic maps and geologic sections earlier in one of the theoretical lessons. Today we are going to have a practical demonstration on this business of preparation of geologic sections. I will also take this opportunity of wrapping up the question set of the previous lesson before we begin with the preparation of geologic sections. This is the question set of the previous lesson. The first question that was asked was whether the following statements are true or false. The first statement was swelling soils are found only in desert. This is more often than not is true. However, swelling soils are also found in non-desert environment, particularly in fine-grained soils where there is a lot of smectite minerals present. Swelling soils could also be present in situations where there are a lot of clay minerals between rock joints. In such situations also there could be a lot of potential for swelling in the shallow layers near the ground surface. And these geologic settings are not necessarily found in desert. They are also found in other hydrometeorologic environments. The second statement that was given was collapsible soils are usually dry. This statement is true because collapsible soils are usually found in situations where the natural moisture content is relatively low, and the soils exist in a moist to dry state. This type of soil typically comprise of situations where you have got weak cementation bond because of deposition or accretion of different types of chemicals at the interparticle contacts, and these cementitious accretions, they tend to get destroyed very easily if the soil is disturbed a little bit, and as a result the soil leads to volumetric collapse, if you recall from what we have discussed earlier in the previous lesson and earlier in this particular course. The second question that I asked was, can a clay silt soil of high plasticity be classified as collapsible soil? If you recall the subject matter of previous lesson, then you will see that typically collapsible soils are not usually not classified as highly plastic fine-grained soils, and they are typically in the low plasticity regime. Then let's move on to the third question. Can a soil with high swell potential be classified as CH? This is a possibility. This is indeed a possibility. Highly plastic soils comprising a lot of active clay minerals such as smectite can be they form a very large chunk of swelling soils with high swell potential. So CH or clay with high plasticity can indeed be a likelihood of the classification of a swelling fine grained soil. Then moving on to the next question, explain the following terms: sinkhole and trough. If you recall from what we discussed in the previous lesson, sinkhole is a situation where a soluble channel forms at some depth near the surface within a volume of soluble rock such as poorly compacted limestone. In such situations, if a cavern forms very near to the ground surface, the overburden above the cavern cannot sustain, it is unstable, it cannot sustain its own weight or the structure that is supported on such covering above the cavern, and as a result the overburden usually collapses into the cavern. As a result, sinkholes develop. Trough, on the other hand, is a little bit widespread phenomenon where the sinking or subsidence occurs over a relatively wider distance scale at the surface of the site, and this occurs primarily as a result of the collapse of a large aerial extent of underground openings such as mine workings, and as a result the relative movement or relative settlement within the inner portions of the trough is relatively small. On the other hand, near the margins of the trough, the relative settlement, relative subsidence, or the vertical displacement expressed as a proportion of the horizontal distance from a benchmark is quite large, only near the margins, not near the middle portion of a trough. Okay, finally the last question, list the typical mitigation measures against subsidence hazard. We discussed about we gave a list of a number of possible mitigation measures. This could be avoidance of the hazard, identification of the areas that have a potential for subsidence, and avoiding those areas for development. Then there could be structural measures such as filling up of the unstable caverns using inert fills or using grouting. So there were several measures that we talked about in the previous lesson when we were considering mitigation of subsidence hazard. Okay, now let's move on to the subject matter of today's laboratory demonstration. What we are going to do, we are going to take a couple of geologic maps in this particular lesson, and we will be trying to form or prepare the geologic sections along two of the transects along these across these two geologic maps. Now what we are going to do, we are going to follow one of the several methods that are used in preparing geologic sections, and this particular procedure is going to be based on strike lines. So we begin with looking at the definition of a strike line. Strike line is essentially a straight line joining the intersection between the line on a geologic map separating two outcrops of separating the outcrops of two different geologic units and the topographic contour of the same elevation. Okay, just look at that definition, and that will become more clear when I take the example of the geologic maps that we are going to consider a little bit later. This definition is for your records. Now let's move on to the geologic map, the first one. So this is the geologic map. All the different geologic units are labeled on this particular map. We are going to hand draw the geologic sections along the thick dash dot line drawn in blue from the left top, near the left top corner, from near the left top corner of this particular map to near the bottom right corner of this map. And actually, before we get into drawing the sections, let me first explain what I meant by strike lines. So you just consider the 2 points which are marked over there by two circular symbols separating units, geologic unit C and geologic unit D. These 2 points, both of them, they are at an elevation of 500 meter, as is evident from the intersection of the line separating geologic sections C and D and the 500 meter topographic contour. So we first mark such points that are available on the geologic map, and then we draw a line connecting each one of these pairs of points, and these lines are called strike lines, and we are going to make extensive use of strike lines, particularly the intersection of the strike line and the line along which we are trying to draw the section, as you will see in the next little bit. So this is the definition of or this is the example of a strike line. Now let me also put up the second geologic map that we are going to consider. Here the section that we are going to draw will be for the dash dot line, which is which actually comes almost exactly from the top left corner of the map to the bottom right corner of the map. And in this case, let me show you a strike line. So here we have got these 2 points, which are again at 500 meter topographic contour, and they are on the separation between the outcrops of geologic unit D and geologic unit E, and again, as we did before, we just connect these 2 points to construct the strike line. Now the difference, this particular example is different essentially from the previous example, in that in here we are going to consider a non-conformal contact which is shown by a thick orange line, and I am going to highlight this particular line here. This is the line that denotes a fault, and we are going to see how we handle a fault contact in this particular example. Okay, so this is the fault that we are going to see when we look at this particular example. Okay, now before I move on with today's demonstration, let me note down, let me formalize the steps that are going to be involved in the drawing here. This is for your records. It will not be very evident, but it will these steps will become clear when we start hand drawing the sections. So what we are going to do, we are going to start with the geologic map, and this map should include the topographic contours as well as the lines along which the sections are to be drawn. Then in the first step, we are going to draw a baseline, above and parallel to the section line, this is going to be going to correspond an elevation which is lower than the lowest elevation encountered along the section line. Then we are going to project the intersections of the topographic contours and the section line up to the baseline. Then we are going to scale off the elevation differences between the baseline elevation and the elevation of the topographic contour perpendicular to the baseline to mark the points along the surface profile. Connect these points to mark the surface profile. Then we are going to project the intersections of the strike lines, which I illustrated a little bit before, for contacts between all pairs of geologic units possible upward to the baseline. Scale off the elevations of the differences between the baseline elevation and the elevation of the strike line perpendicular to the baseline. Connect these points to mark the profile of the contacts between the pairs of geologic units, and then mark the locations of non-conformal contacts such as faults and dikes, if any, and show their dip if available from supplementary data. Now these are just a few statements. This slide as well as the previous two slides, these actually give you a synopsis of what is going to happen in the next little bit when we start drawing the geologic sections. So now I am going to also show you the result that we are going to get. So this is the first example that we are going to consider, and here I have rotated the map in fact so that the section becomes horizontal actually on this particular slide, and the section, geologic section, that is going to be prepared from this particular drawing is shown up above of the geologic map. So this one here, this one here is the plan or geologic map section of the geologic map, and up above is the geologic section that we are going to draw in this demonstration, geologic section. So this is the first example. Then in the second example we have this geologic map, the one that is shown at the bottom. So this is our geologic map of the second example, and the section is shown up above. This is the geologic section that we are going to prepare in the next little bit. Okay, so with that I'm going to wrap up the presentation part that comes really as a preamble to what we are going to do next, and just now we are going to start drawing the geologic sections. You just hang on with us, you just keep watching what is going on. I'm going to keep explaining what goes on during the preparation of the geologic sections as it happens. So we are going to wrap up the first part of this presentation with this. Okay. So here is the drawing. Here is the geologic map that you have already seen. What we have done in order to save a little bit of time, we have already drawn the strike lines, and we will begin with labeling the strike lines in order to let you understand what was done before. So for example, the strike line on the left here, which I am going to label, it connects the interface between B and C at elevation 400. So let's label this one as 400 BC. Then you can tell what is the next one. The next one actually connects again the interface between B and C, but that is at an elevation of 500 meters. So this one is going to be labeled as 500 BC. Then moving on to the right, the next one up is the interface again between B and C, and that one is at elevation 600. So we are going to label this particular strike line as 600 BC, and then we move on to the interface between units C and unit C and D. So here the first one is the strike line at elevation 400. So we are going to mark that one as 400 CD. Then moving on, the next point on the interface between C and D is the strike line at elevation 500. So that's going to be 500 CD. Further to the right is 600 CD. Then we move on to the interface between unit E and unit D. So here the first strike line is at elevation 600. So this one is going to be 600 DE. Next one, what we have done here for the next one is that is actually the interface between D and F, unit D and unit F. The strike line is at elevation 400. So accordingly we are going to write that one as 400 DF. Then further down to the right is again back to the interface between unit E and unit D. So for this one, actually what we have done is to interpolate between contours of 500 and 600 meter elevations to obtain a subsidiary point at 550 meter elevation. So accordingly this particular strike line is 550 DE. Next one up is the interface again between D and F. This strike line represents elevation 500. So we have got 500 DF. Then a little bit further to the right is the interface between units E and G, and this particular strike line represents elevation 600. So this one here is going to be labeled 600 EG. And then the last one here is again between interface of units E and G, and for this one again we have interpolated between elevation 600 and 500. So this one again is going to be noted as 550. Like the earlier interpolated contour, it is going to be noted as 550 EG. So that is that's all about the strike line. So now let's move on to the preparation of topographic surface. So for that we are going to use a tracing sheet like this one, which is marked with which is a graphical tracing sheet really. So what we are going to do, we are going to club this one on with the map like this, so that the graphical markings, they are parallel to each other, they are parallel to the section, let's paste it. And now we proceed with the drawing first of the surface of this particular section. So let me position this map a little bit. So our baseline here is going to be along the section line itself, and since the minimum elevation that we encountered along the section line was 300 meter within the main body of the geologic map, so let's consider this particular baseline to be at an elevation of 200 meter, and then we are going to use a scale of 10 millimeter equal to 100 meter in the vertical direction, and in the horizontal direction we are going to use a scale of 10 millimeter equal to 250 millimeter. That is going to give us a little bit of exaggeration in the vertical direction and topography, in order to enhance the topographic features a little bit. So you should realize that in the vertical direction we are going to use a scale like this. So this one here is going to be in our case 200 meter, and in the horizontal direction we are going to similarly have this much of distance equal to 500 meter. So these are the scales that we are going to use in this particular section. So this one here is horizontal and this one here is vertical. All right. So this here, as we have mentioned, the baseline itself represents 200 meter. So we are going to base our construction accordingly. All right. So let's now begin by marking the locations of the topographic contour. So first intersection of the topographic contour is at the corner, at the area which is a little bit outside of the range of the camera. So let's begin with the intersection between the section line in the geologic map and the topographic contour at elevation 400. So that is this particular point here. So 400 then is going to be as far as our scale is concerned, it is going to be at an elevation of at a distance, at a vertical offset of 20 centimeter according to the scale that I have drawn. So that is going to be the point on the surface there. The next one up is the 500 contour, and 500 contour is it intersects the section line and the baseline at this location here. So we are going to project that one upward 30 centimeter, and accordingly we are going to have a point on the surface out here. Actually, let me yeah, that's right, it is going to be right about there. Okay, then next intersection between topographic contour and the baseline as well as the section line is out here, and this one is this one represents the contour at 600 meter elevation. So that one is going to be at this location on the section line. Going further to the right, 600 meter elevation contour again cuts the section line and the baseline at this location. So we project that point up to obtain another point on the surface at this location. Then we get to the topographic contour of 500 meter elevation, and that is at this location, project it up just like what we were doing before, and we get a point out here. Again we get an intersection between the section line and topographic contour 500 at this location, project it up, and we get another point here, and finally we may consider the interpolated contour of 550, which approximately cuts the topographic contour at this location, and thereby we are going to get a point which is going to be approximately at this location. So that's, then we are going to join these lines, these points, to obtain the surface profile by a smooth line, actually, to obtain a surface profile like this. And that is going to be our surface, that is going to how the surface is going to look like of this particular area on the section drawing. All right, now let's mark up the outcrops which are going to appear on the section. So what we are seeing here is that up to here we are going to see we are actually intersecting, we are transecting unit B. So unit B is going to continue all the way from left on this section to this point here. Then we get a little bit into unit C and project the area or the length of the section line which is covered by unit C, and we get to there. So this part here is going to be unit C, and after that we move on into unit E, and we remain in unit E until we reach this point. So from here to here we are going to see exposure of unit E at surface. Then we get a little bit of unit, which unit is this? That one is unit F. So we are going to see a little bit of unit F up to this point at the saddle portion of this topography. So this is unit F, and finally we get into unit E. Okay, so those are the outcrops that are going to be visible at the surface. Now let's start projecting upward the intersection between the strike lines and the section line. So what we are going to get, the first one is 400 BC. So that is the intersection between units B and unit C, and it is at an elevation of 400. So that is at this location here. So that one there is going to be right near the surface. So this particular point we are going to mark again as 400 BC. So that is going to give us the interface between units B and unit C, and that is at an elevation of 400. So then, since it is such a thin layer, we are just going to actually we have got other points of intersection of the interface between BC. We have got another point here which is at 500 meter elevation. So we move up to here approximately, and that is going to give us 500 BC. And in fact we have got one more, and that is at 600 meter elevation, and that is almost near the no, that is between C and D. Sorry, we are going to just connect the interface, the outcrop, the line separating the outcrops of B and C between these two these two projections of the strike lines, and that is going to give us the interface between units B and C. So unit B is going to be at the top, and unit C is going to be underneath that. Okay, so this is going to be the shape of unit. So this is going to be unit B, the one that I am hatching right now, the thin one, thin veneer, and underneath that we are going to get unit C. So let's now delineate the bottom of unit C. So let's look at the interface between unit C and D. So in order to do that, we are going to follow exact same procedure. Now we are going to project the strike lines that represent the interface between unit C and D upward. So let's start doing that. So the first strike line that represents the interface between unit C and D is this one here, this one. That is the intersection between the strike line and the baseline as well as the section line. So this particular, let's project this particular point up, and this is the point corresponding to 400 meter elevation. So we are going to go up to here, and that is going to give us a point at the interface between C and D and at 400 meter elevation. So we are going to mark that one as 400 CD, and then we move on to the other point representing the interface between C and D, and that is the strike line. That is the location of the strike line where it intersects the section line as well as the baseline in this case. This represents elevation 500, so project that one up to 500 meter elevation, and we come to a point which gives us the interface between units C and D at 500 meter elevation. So that is going to be 500 CD. Then we have got another point which represents 600 meter elevation at the interface between C and D, and that is the point where it cuts the where the strike line corresponding to this elevation cuts the section line as well as the baseline. So that is at elevation 600. So this is going to be 600 CD. It's becoming a little bit busy now with so many points appearing on the section. And I think that is the last one on the interface between C and D. So we are going to join those 3 points, and what we get is a line like this one, and below that is going to be unit C, and above that is going to be unit D. Now you will ask, what is going to happen to this particular line? We are not going to project this line all the way to the surface in this particular case, because along the section line unit D is not going to be visible, and it is going to be covered. Actually, if you see the geologic map, then it is going to be covered by a thin veneer of unit E. So this particular line which separates unit C and D is not going to move on to touch the surface, and it is going to intersect the interface between D and E instead. So now what should we do? We are going to start marking up in a similar manner the interface between the profile of the interface between D and E. So this is the strike line intersection for elevation 600 and the section line. So project that one up to 600 meter elevation. So we come to this point, and this is going to be 600 DE. So in fact that is going to demarcate, if you realize, that is going to demarcate the top surface of the of unit D. Okay, now let's move on to the next strike line demarcating the intersection or the interface between D and E, and that is this one here. This represents the interpolated contour of 550. So let's project it up to 550, and we come to a point which is roughly here. So that is where we are going to get 550 DE. So this one is going to give us 550 DE, interface between D and E at elevation 550. So let's connect that one also. So that is going to demarcate the top of unit D, and we can actually project this particular line backward, because we know that unit E starts from this location, because that is the interface, that is the limit of the outcrop of E, and we also know that the outcrop of E ends at that point. So we can connect those 2 points, and above this particular line is going to be unit E. Let's label this one up so that it is visible. So this one here is going to be unit E. That is how unit E is going to look on the section. Okay, now back to the other interface, the other interfaces. Now we have got we are going to get another one to the right, further right, and that is going to be between E and G. So let's consider those strike lines. So this is the strike line at 600 meter elevation between E and G. And project this one up to 600. So that is going to be the point where E and G is going to be separated. So this is going to be 600 EG, and we have got another point further right that is going to be at 500 EG, and that particular point is going to be further to the extreme right of this particular section. And if we join that, then we are going to come up with the profile of the interface between E and G. Above this particular interface will be E. So this one marked by green hatching is going to be unit E, and underneath that is going to be unit G. All right. Now let's go back and see whether we can get any more information from this particular. Okay, let's first actually crosshatch the unit C by green. So I'm going to use green in this particular case. So this is going to be our unit C. It's going to look like this. So that is our C. B is out here. E is back there. And F is actually unit G is to the right. No, this is actually unit E, sorry. This one is unit E. And underneath that is going to be unit, underneath this one is going to be, let me have a look. What do we, no one, okay, underneath that one, underneath G, sorry, this one is going to be G. This one is going to be G, and underneath G is going to be unit E. So that's how it works. So further, actually, this is going to be G, I think. This one here, I marked it, I labeled it in a wrong manner, is it? This one here is going to be, which unit is this? F, and then we are getting back into unit E, sorry. So that's how it is going to be. So we are going to get a little bit of unit E, further to the right. So this is going to be our unit E, and that is not unit G. So this is going to be unit E. So unit E is going to be here and here. So these are the units that we are looking for. So this one is unit E. Okay. So unit E was near the middle of the section, and as well as further to the right of this particular section. All right. Now we also will get another we could actually get another strike line if we interpolate some of the topographic contours for the interface between actually unit F and underneath F is the major unit here is at the top of F actually. So we are going to get we have got a few more strike lines actually. We have got the strike line here which we missed, which separates the units D and F, and this one was at elevation 500. So let's draw this one. So that is going to be 1 2 3, this one here, so that is 500 df. So that demarcates the top of unit F, and we just do not have any we have got another interface, another strike line corresponding to the interface between D and F, and that is this one. This is at elevation 400. So we come to a point here, so that is going to give us the interface between units D and F. So above this one is going to be unit D, and underneath this one is going to be unit F. So this one is going to be our unit D, and underneath this one is going to be unit F. Okay, so that kind of completes the section, whatever information we could get for the example that we considered to begin with. And now let's move on to the next example. So here again we have marked the section lines, the strike lines, and again you have to find out the you have to actually label the strike lines and project the strike lines up to the appropriate values to demarcate the interfaces between units C and D in this case, because the strike lines that are bunching here, they represent the interface between units C and D, and the strike lines that bunch out here, they represent the interfaces between units D and E. So you have to appropriately label the strike lines, find out the intersection of the strike lines, and project it upward to appropriate elevation. Similarly, here you have got the strike lines giving the demarcation between units E and F, and finally what we got here are a couple of strike lines obtained after interpolating the available topographic contours, and that gives us the interface between F and G. So we follow the exact same procedure as I explained in the preceding, and what we are going to get in the process by doing the necessary exercise is to construct a section like this one, and what you can see here is that the available information is rather tenuous, so that we could actually draw the sections only to little bit limited depth in this particular case. So let's mark the units anyway on this particular section. So this one is unit A, and after that we got into unit B, and then this one is unit C and D and E, F and G, and then we hit the fault line. We hit the fault line, and finally on the other side of the fault line we get back into F. Now you notice here that we have drawn the fault line in a vertical manner, because that is going to be most probably the case, because in this particular section the fault line actually follows a straight, it follows a straight geometry in plan, and if that happens, then more often than not the fault line actually dips very steeply. As a result, we assume that the fault line in this particular case is vertical. But in general, in order to resolve the dip of the fault, you need the you need actually some additional subsurface boring information in order to confirm the inferred dip of the fault line. So this gives you some idea actually about the geologic map preparation, and I left the large part of the second example for your practice. So you try to use this as a as an exercise and try to get I gave you the solution as well, so you try to complete the section at your own leisure and try to see whether your solution matches what is provided on this particular example here. Okay, thank you very much. Until we meet the next time, and that is going to be an outdoor session where we are going to demonstrate the laboratory procedures and some of the field procedures for characterizing soil and rock samples. Okay, until then, thank you and bye bye. Here we are going to give the demonstrations on different simple laboratory testing for classification and identification of key soil parameters and rock parameters. So with that said, we are going to move on to the first laboratory experiment involving sieve analysis, which is carried out to find out what is the distribution of grain size or representation of different grain sizes within the soil matrix for coarse grained soils. These are the IS standard sieves used for finding out the grain size distribution, as I was saying before, for coarse grained soils. What we have got here is a stack of different standard sieves which has got different opening sizes mentioned on the labels here, and you can see the opening of individual sieve from this coarsest sieve that is shown, that is being shown now, and we can show now what is the appearance of the finest sieve used for finding out the grain size using sieve analysis. This is the 75 micron opening size sieve, whereas the first one that you saw was it had an opening size of 4.75 millimeter, as is mentioned on the label. And now you can get the idea, and you look at the labels of different standard sieves, and you can see that it actually goes down in size from the top, starting from the top, or the coarsest sieve is at the top and the finest sieve size is at the bottom, and at the bottom of the 75 micron sieve is a pan which will collect all those soils, all those particles which are finer than 75 micron.